So we're going to start here, and we're going to look at the first case when no shocks are formed, and then we're going to talk about the shocks. So shocks are basically nothing more than when the characteristic lines meet. So for us to have no shocks, we're going to assume, I'm just going to read from the notes here, because it explains it in these pictures really clearly. So we're going to assume the velocity has this linear profile, and we're going to do a calculation with no shocks. So for the no shocks to form, we need the density to monotonically decrease, because that way the slopes are strictly increasing, and you can see that here in this picture here. So the characteristics here have slope 1, and here they have slope -1, and then in this region where it changes, the slope increases. So these characteristics are never going to meet. And this corresponds to a traffic light. Right? All this traffic's parked here, and this traffic there's no cars here, and they're zooming away. And so this is the picture here showing you the evolution in time as it spreads out. So it goes. So these cars, eventually this car's finally waiting at the traffic light, waiting, and then finally gets to drive, speeds up, and drives through. Okay, and if you watch the density here at this point here, it slowly goes down, right? The individual cars are moving through here. Okay, so this is the density at a given point. It's not the actual cars themselves that we've got an equation for. Okay, so that's that. Now we're going to do this problem of the Riemann expansion fan and do a little calculation. So what we've got is the expansion fan is a situation where we've got sort of a limiting case. The initial density is rho L for x is less than 0 and rho R for x is greater than 0. So, and we've got to have, this is the monotonically increasing, so we want rho L to be greater than rho R. So we draw a picture of that. The initial density, the initial density looks like that. And this is rho R. Oh, this is rho. Okay, so what happens is the characteristics here have, coming out of here, they have constant slope. And then coming from here, they have constant slope like that. Okay, and then the question is what happens in the middle region here. It doesn't have to be the case that these are negative and these are positive. It's just that this positive. The slope has to be greater here than greater on this side than on this side. Okay, so we've got to go and understand this curve here. So on this curve here, what happens over here? So on the characteristics, what do we have? We've got x is equal to x naught So on this characteristic here, x is equal to x naught plus rho, the c of rho r times time. Okay, now of course on this characteristic, that's the equation here, or rho left if we want. So on this curve here, x naught is equal to 0. So x is equal to c rho r t. And likewise here, x is equal to c of rho left t. So immediately we can see anywhere on this side of this curve. So the density going forward in time is going to be 3 regions. Here it's a constant, it's equal to c, still the c rho r. It hasn't changed. So over here the density continues to be rho left. And we have x must be less than c rho lt. And then we have likewise rho r is if x is greater than c of rho rt. But the question is what happens in the middle in this expansion fan. Okay, so this is this region here. What happens here? So, in this region here, we still have x is equal to c of the density times time. So now we need our equation of state. So we assume that c is equal to v naught rho max minus 2 rho over rho max. And then we can then say that, so that's c. So we solve that equation, and we turn this equation around, substitute this in, and we solve for rho. Okay. Maybe we can write it out here. So if c is equal to that, then ct must equal x, and then we solve for rho. And we get rho is equal to a half rho max 1 minus x over v naught t. So then in this middle region, on this expansion fan where all these straight lines come out, and in fact the density just goes linearly down from across this expansion fan, but the formula is a half rho max 1 minus x over v naught t. And that is for x is between, so x is greater than c rho lt and less than c rho r t. So that's the expansion fan, and then I'll just show you that quickly on the computer. So here's the solution. So we've got 0.6 and 0.3 density. There are the characteristics. There's the expansion fan, and there's the solution going forward. Okay, and since the 0.6 is slightly further, closer to 0.5, this expansion fan is steeper. This characteristic here is steeper than the ones here, so this point moves away faster than this point here. But at some change, abrupt change in density, so you've got cars at a certain density moving slowly here, and these cars are moving faster, and then this is the region where they speed up, and it slowly smears out over time. Alright, so now the only thing we've got to deal with now is shocks, and we've finished the course.